All right, folks, today we're going to start a completely new subject. We're done with the gerrymandering. Actually, we're done with the sort of politics topics entirely. The whole first half of the course was about things that are vaguely related to politics. Not vaguely, they were related to politics. The rest of the course is going to be some other stuff that's got nothing to do with that other stuff. What we're going to start talking about, this is our next major unit, is something called graph theory. Graph theory. This is something that likely you've never talked about in a math class before. Probably you have talked about things like the graph of a function, the graph of, a line, or the graph of a parabola. This is not that. The word graph here does not refer to the graph of a function. It refers to something completely different, which we use the same word for. It's also called a graph. Anyway, a graph is a thing. So graphs are things like, I will draw an example, something like this. It's a sort of a diagram, which is made up of dots and lines connecting the dots in certain ways. This is an example of a graph. So this, I just want to talk about some basic terminology about graphs, and then we're also going to talk about why mathematicians care about graphs. It turns out, talking about graphs, there are many applications of graphs in the real world, and so we're going to talk about some such things. First of all, terminology. The two basic terms that we use to describe graphs is, I just said a graph is like a thing like this, which is made up of dots and lines. We don't use those words, dots. The dots here are called vertices. Well, an individual one, the singular of this word is vertex. So each of these things is a vertex. Plural is vertices. All right. So this graph right here, it has how many vertices? 1, 2, 3, 4, 5, 6 vertices, right? Those are the dots. And the things connecting them, the lines, they are called edges. So a graph consists of vertices and edges, and the edges are, these lines like that. All right, this is not that complicated. There's vertices and edges. So how many edges are here? You can count them if you want to. Notice you are allowed to have two different edges between the same two vertices if you want to. That is allowed. And also, a vertex can have one edge that just kind of goes back to itself. That also is allowed. All right, let's talk about some more interesting terminology, perhaps, and then we'll get to talk about why these things are useful for anything. All right, one very important concept in graph theory that comes up a lot in the applications of graph theory is what we call the degree of a vertex. So every vertex in the graph has a degree, and the degree is a number, and the definition is it's the number of edges meeting that vertex. Number of edges meeting that vertex. So could we draw just right here the degrees? Each of these vertices has a degree. What is the degree of this one? You just look how many edges are going into this vertex, and the answer is 2. So that one has degree 2. How about this one? 1, 2, right? This one also has degree 2. It's how many edges are going into that vertex. This one right here, how many edges are going into this one? I see 1, 2, 3, 4. So that degree is 4. This one up here, it looks like 3 to me, right? 3 edges meet this vertex. This one over here would be 2. And this one over here, this is a little technicality in the definition. The degree here counts as 3. So even though I said it's the number of edges, and I suppose this one you might say this edge is really the same as this one over here, it still counts as 2 separate contributors to the degree. So this one has degree 3. Really, technically, you might say it's the number of ends of edges which meet that vertex. So this vertex has 3 edges coming out of it, 3 ends of edges. Now the fact that these two are actually the same edge is irrelevant. The degree there is still 3. All right, this is what the degree means. They're just numbers. Very simple concept. It turns out, though, to be very important in many of the applications of graph theory that we are going to talk about. All right, some more very simple terminology. How about an edge like this? Actually has a special name. An edge which starts at one vertex and goes and just comes back to the same vertex. That is called a loop edge. Oh, my marker's doing great right now. A loop edge is an edge from one vertex to itself, right? That's called a loop edge. What else? Simple terminology. There's no real surprises here. A path. I'm going to erase this now just so I can continue my list. A path. A path is just sort of a bunch of edges one after another. It's what you think a path should mean. You start at one vertex and you go through the graph by following edges one after another. So a path is a sequence of, I'm going to say it is a sequence of vertices connected by edges. So what I mean by that is, for example, if I have a graph like this, and maybe it has edges like this. How about this is, I'm going to say A, B, C, D, just to give the vertices names. Sometimes when you describe these things, you want to have names for the vertices. So in this case, A, B, D is a path. And on the picture, this ABD represents you start at A, then you go to B, then you go to D. Actually, let's put in a C there. That is also a path, right? You start at A, then you go to B, then you go to D, then you go to C. That's a path. All right. Here's something that's not a path. A, D, C, B. This is not a path because you actually can't start at A and then go to D and then C to B. Actually, the C to B is fine. You can go from D to C to B, but you can't go from A to D. So this is not a path since there's no edge from A to D. And so you can't actually this doesn't actually make a path because the A and D, there's no actual connection from A to D. All right, if you really wanted to do something like that, you'd have to go through B first. So you could do A, B, D, C, B. That would be a legal path. All right. How about a circuit? A circuit is just a path which kind of goes around in a circle. Now, it doesn't have to literally look like a circle. What I mean by circle is just that it ends up at the same place where it started. So a circuit is just a path with the same starting and ending vertex, right? A path is one which starts at some vertex and goes and ends up at some other vertex. It's called a circuit if the starting vertex is the same as the ending vertex. Okay? Not a lot to say about that. And then one last thing. I hope all of this terminology is pretty straightforward. Even if I didn't tell you what a path or a circuit means, you probably would guess the same thing that I just said. One last definition, which is, again, very intuitively clear, although not so easy to say really how you should write the definition. The term is connected. So a graph is connected when, I'm going to fill in the blanks here, leave a little blank spot there. What it means in sort of intuitive language is just that, like, it has, when you consider the graph, it's all like in one piece, like one chunk. So for instance, actually every graph that I've drawn so far is connected. This one is connected because it's all one thing. But an example of one which is not connected would be something like How about that? If I consider this as a graph, This right here, this is not connected because it has like two pieces. You might wonder, does that even count as a graph? Maybe that's just not a graph, that's two graphs. Well, no, it does count as a graph. We just call this one a disconnected graph or a not connected graph. How are you going to make that definition? Is there anything you can say, like in real terminology, for example, using the terms that I've already given definitions to? How can you say exactly what it means to be connected? You can't just say like, well, it only has one piece, because the word piece, I didn't actually say specifically what that means, right? I didn't give a definition to the word piece. Actually, the definition for connected is done in terms of paths. So one thing which is true of a graph which is connected, it looks like this. One thing that is true is you can always get from one vertex to another in this graph along a path. If you choose any two vertices, even if they may not be connected by an edge, for instance this one and this one, they don't have an edge together, but you can make a path from one to the other. That is not true of a disconnected graph. For instance here, from this vertex to this vertex, there is no path that goes from there to there. That's how you know it is not connected. So the true definition of connectedness is about paths, and I'm going to say a graph is connected when any two vertices, I'm often going to write verts, any two verts can be joined by a path. All right? And here I did not use any undefined terms like chunks or pieces. Now in your mind, in your heart, you should feel like connected means there's only one piece, or you can't split it apart into two chunks, right? But you don't want to use those kinds of words when you're writing the definition, because those kinds of words are not defined yet. So this is what connected means. Any two vertices can be joined by a path. I hope that these things are all very intuitive. Let's talk about how are graphs used in the real world? Graphs in the real world, actually graphs are used all the time to model real world phenomena. I think graphs are actually interesting in that probably most of the mathematics that you've learned in your youth is mathematics that was created in order to do science, specifically physics. Calculus, pre-calculus, if you ever learned geometry or trigonometry, those things are generally applied when you're doing physics or some kinds of engineering, building things or analyzing things in the natural world. You use algebra and calculus and that kind of stuff all the time to do those. It turns out graph theory is most useful used for, I will say, not so much phenomenon of the natural world, but graphs are used in more like the social sciences rather than the physical sciences. I'm going to say they're used for kind of social phenomena rather than physical phenomena. This is not a hard and fast rule, but it is true generally that the applications of graphs tend to be for sort of man-made things or man-made structures, societal structures. Anyway, let's talk about some examples. So some things, areas of your life where you have encountered things which are very similar to graphs. One would be something like road maps and navigation, right? This is something that we used to have to do by hand, but now our phones do it for us. If you use Google Maps or whatever on your phone or on your computer, it probably isn't really happening on your phone, but somewhere on the internet, somewhere in some big computer somewhere, there is stored a complete picture of what every road everywhere looks like, and they look sort of like this. If you're in a real city, then they're on a sort of rectangular grid typically. If you're somewhere else, they have lots of turns and twists to them. But anyway, and in these systems, which are trying to give you directions, there's always like, you're here, and where you want to get to is over here. And you sort of push the button, and the computer figures out how do you get from here to here. And what the computer has to do is it thinks of this road map as basically a giant graph where the roads themselves are edges, and then each intersection is like a vertex. And then it tells you directions based on finding a good path in that graph. So road maps and navigation, specifically navigation, is about finding paths, right? And in general, there are many paths to get from one place to another. There are many ways you could do it. You trust the computer to try to find the best path, and that's actually a specific thing that we're going to talk about later on. But this is one major application of graphs. Here's another. Here's another application. How about airline routes? Now this will seem kind of similar, and it is really very similar to navigation on roads, but there's an important difference that I want to mention. So an airline route, if you ever flown on an airplane and you see like they give you the free magazine with a bunch of, which is not interesting at all to read, but the magazine that you look at in the airplane always has a map of the U.S. and all of the airline routes that airline travels. And so, you see something like this map of the U.S. There's my representation of the U.S. And there's like certain cities marked on the map, and these are wherever the airports are, right? And then there's a bunch of lines on the map. They look like this. Maybe there's a line there, maybe there. There's lots of lines here. And you can sort of see how big a city is, or at least how big the airport is, based on how many lines you see. Like here, this is like, I'm imagining this is New York. And then here's Los Angeles. And there's a line going from there. That means that there is a flight that goes from New York to LA. Here's, I don't know, Seattle maybe, and there's, less flights because Seattle is not such a big city. And maybe there's like Denver is here, and that has a lot of flights because Denver has a huge airport, right? I'm sure you've seen maps like this. What is interesting about this kind of graph, so in this graph, each vertex represents a city, and each edge, I'm going to write this down actually, the vertices are cities, and edge is a flight. So the fact that there is an edge, say from here to here, maybe this is New York, and I don't know where that is, somewhere in Mississippi, maybe Alabama, Birmingham. The fact that there is an edge right here means that there is a flight from New York to Birmingham, right? What's interesting about this graph, the way when you see this graph, a picture of this, it doesn't actually mean that the plane literally flies in this exact way to get from one city to another, right? The actual route that the plane flies is probably, it's probably pretty close to that, but it doesn't really follow exactly this path. The plane is gonna, just because of weather or whatever, the plane will swerve around a little bit, and on these longer flights, there's no reason that it's gonna go the same exact way every time. It won't go the same exact way every time. So the edges, they are not actually meant to represent exactly where the plane goes. They just represent connections. And this is a theme in most graphs. This is not really true of the road example that I said before, but most graphs are not actually meant, the edges themselves are just meant to describe the fact that there is a connection, that the edge doesn't really tell you any more information than that. It's not meant to suggest that the plane really goes there. So the edge is a flight, and I just want to point out, in a graph, edges indicate connections, but usually not specific geometry, right? what I mean by they don't indicate specific geometry. What I mean by that is just this line here is not really meant to indicate that the plane actually flies along that line specifically. It just means that there is a plane which goes from here to here, and there's some connection. But the line itself is not meaningful as a geometric line. That's what makes graph theory different from other types of geometry. You notice that we will never talk about things like angles of lines or how curvy the line is, or even how long the line is. None of those things are relevant in a graph in the typical usage of graphs. All right, what else? All right, here's something a little bit more abstract. How about computer networks? Probably when computer networks are described, they basically are always described in terms of graphs. For instance, like a diagram of the internet. If you've ever seen a diagram of the internet, I mean, on a small scale, it looks something like you just have a bunch of different computers. So the vertices here are computers, and then the edges are connections between the computers. All right, and so if you want to say this is my computer, me, and I want to send an email to my mom's computer down here. You know, when, I don't know if you ever thought about this, but when you send an email to your mom or whoever, wherever you're sending from, let's say you're sending from your computer, your mom's going to read it on her computer. Your computer doesn't actually send the email directly. What happens is you write the email, you hit the button, it goes to some server somewhere. Now I use the Fairfield University email for most emails that I send, and actually I believe the Fairfield University emails are actually run by Google. So when I send an email, the first thing that happens is it goes to some Google server somewhere, which is not physically located. I don't even know where it's physically located, and it doesn't matter. And then that Google server will send it to whoever is in charge of my mom's email. Let's say my mom uses, Yahoo or something, because she's old and she uses Yahoo. So the email goes from my computer first to some Google server somewhere. Then from Google's computer, it goes to some Yahoo server somewhere. And then finally, Yahoo will deliver it to my mom wherever she is. So I just described really 3 steps in that procedure, right? To get from me to my mom. And these individual steps, they represent, like, they do exist kind of in the real world as physical wires. But even when you're going from my computer to Google or from Google to Yahoo, there may be many intermediate steps that it has to go through in terms of actual physical wires. And this is a major problem actually on the internet. Every time you want to send anything on the internet, this includes emails, but also just like if you want to visit a web page, the web server, wherever that web page is, has to send its information to your computer so that you can look at it. All that stuff, it has to find a path through this massive network of which is really a graph. So any internet communication must be, and there's a word which you probably heard in this context, must be routed through a path in a graph, right? Routed. There are, physical devices called internet routers, and their job is just to efficiently figure out which way to send the message. To get from me to my mom, they figure out how many intermediate steps does it have to go. And just like in a road network, there are many possible ways that you could decide to route the message, but they want to somehow figure out what the best way is, or at least a pretty good way. And anyway, this kind of thing is happening, millions of times per second all around us. And these edges here, again, I will just emphasize, the edges do not actually represent straight lines that exist in the real world. Some of these will be physical wires that are not straight at all. They wrap around things or whatever. Some of them don't even represent physical objects at all, like when you're doing this from your phone, or if one of these connections is over a Wi-Fi network, that's not even a physical thing at all. One of these edges might actually represent a wireless connection, or some other things, right? Anyway, this is modeled using a graph, right? And the actual geometry of these lines is actually very far removed from what is really happening in the real world. All right, one more. How about social networks? This is yet another level of abstraction away from real physical things. Social networks, I mean, like Facebook or Instagram or whatever, Twitter, these kinds of things, they also function like graphs. I'll just take Facebook as an example. I know because Facebook is kind of a simple example. On Facebook, the vertices in this graph are people who have Facebook accounts, and like some of them are connected to one another and some of them are not, according to who are friends, right? So on the Facebook, and when you think of this as a graph, the vertices are Facebook users, right? And edges connect friends. So if you are friends with somebody on Facebook, you and that person are like two little dots in their graph, and they put an edge between you to represent the fact that you are friends on Facebook. Now, really all sort of social media works in roughly in this way, although other systems like on Twitter, you don't have friends. People can follow other people, and it's possible on Twitter somebody can, like I could follow you even if you don't follow me. And then that doesn't exactly fit into a graph because those are like one-way connections, whereas on Facebook, it really does make a very simple a graph in the way that we're talking about it, because on Facebook, for two people to be friends, they are actually friends both with each other. You can't be someone's friend if they're not also your friend on Facebook, right? On Twitter or something where you have one directional, that's called a directed graph, where all the edges have directions to them. This is called, what we're going to talk about mostly in our class is undirected graphs, which Facebook is like that. All right? All right, I think that's enough examples of this. I hope you get the sense that graphs are the appropriate thing to use for many, many situations. Just so we get a feel for this, I'm going to do several examples of the general format of, imagine there was a graph that represents blah, 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 and then can we talk about, is the graph connected? What about the degrees of the vertices? Are there paths or circuits or whatever? All the basic terminology that I talked about at the beginning. Erase that. All right, here's first example. I got several examples. These are made-up examples. How about, let's consider a graph with a vertex Consider a graph with a vertex for each of my kids, and their ages are 3, 7, 12, 12, that's the twins, 18, and 19. All right, I don't really have 6 kids. I have 2 kids. They're not twins. This is a made-up example, all right? It's make-believe. This is not real. I don't want 6 kids. Let's consider a graph with a vertex for each of my kids. I don't really have this many kids. And let's say that my kids have these ages, and let's say also that 2 kids are friends when their ages are within 5 of each other, right? It's hard for a 3-year-old to relate to a 19-year-old, but the 7s and the 12s, they can just barely get along, all right? Can we represent this on a graph? I think we can. We can draw a graph where each of the kids with the various ages are vertices. I already said that, a vertex for each of my kids. And then let's represent the friends, this relationship, the friends, by edges. Can we do that? And maybe I would like to ask, can we say some things about that graph? Like, is it connected? And so on. So I have 6 kids here. So I'm just going to make, I don't know where the edges are going to go really, but I'll just put 6 dots here and I'll fill in the edges when we get to it. And I'm going to label them according to these ages because each one represents one of these. So I'm going to put 3, 7. Now there are 2 age 12s, but you know, that's all right. They're going to be kind of indistinguishable in the graph. 18 and a 19, right? And now, where do the edges go? I said 2 kids are friends when their ages are within 5 of each other. So you just have to look through this and ask yourself, where should I put edges? For the 3, are there any edges connecting the 3 to anybody? Yes, the 3 has an edge with the 7 because their ages are within 5 of each other. So there is an edge here. How about the 7? Well, the 7, of course, is connected to the 3. The 7 also is connected to the 12. I said within 5. What I meant was 5 or less. So 7 is connected to the 12. And of course, the 7 is also connected to that 12 because they're both 12, right? That's the twins. What about 7 to 18? No, that's they're not within 5, and there's no edge 7 to 19 either. All right, how about the 12s? Well, the 12s are connected to the 7. The 12s are also connected to each other. There should be an edge there. They're definitely within 5 years of each other. Is there an edge 12 to 18? No, that's 6 years, which is too much. This 12 also, no edge there. Actually, these are all the edges for those so far. There is an edge between 18 and 19, and that's it. All right, so this graph describes all the friendships, and you can see, what can we say about this graph? Well, we can say it is not connected, right? Not connected, all right? Are there applications of the fact that this is not connected? I don't know. You could say something like, if I want to tell all my kids to brush their teeth tonight, could I just tell one of them and say, hey kid, brush your teeth, and tell all your friends to brush their teeth too? Actually, the fact that this graph is not connected means that strategy is not going to work. Because if you tell, say, the 12-year-old, brush your teeth, and then tell all your friends to brush their teeth, the message is only going to get to these people over here. It will never get to those people because there is no path among friendships from the 12 to the 18, right? The 18 and the 19 will never get the memo. All right. I don't know if that's, is that cute? Let's try another example. I want you to be comfortable translating a real-world scenario into a graph and vice versa. That's why I'm talking about these examples. This is a silly one. They're all kind of silly because I'm a silly guy sometimes, especially when I got to stay home for weeks at a time and I got to teach my class in the basement. Okay, here's another one. Let's consider each vertex is a Hollywood star, famous actor, all right, and two stars are connected by an edge if they have been in the same movie together. If they've been in a movie together, all right? I want to imagine what this graph looks like. Now, in this case, you can't just draw the whole graph because there's you know, hundreds of Hollywood stars, thousands maybe. And the graph will be way too big for you to draw and see the whole thing. But we can kind of think about what this would look like and ask ourselves some questions. One question that I want to focus on is, what is the meaning of the degree of a vertex in this particular graph? All right, but let's first think about, so just to get an idea of what the graph looks like, each vertex is an actor. So maybe, I'm going to go over here. Maybe here I have Chris Evans. Remember him? Captain America, right? And then who has he been in a movie with? He's been in a movie with many people, I guess, but among them, how about Scarlett Johansson? Scarlett Jo, I don't know how she spells her name. I'll ask her next time I see her. They were in all those Avengers movies together, right? She's the Black Widow. So there would be an edge from Chris Evans to Scarlett Johansson. Is that the only edge from Chris Evans? No, Chris Evans will be connected to many other people in the graph. All the other people that he's ever been in any movie with. Even the Avenger movies, there's more than just Scarlett, right? And then Scarlett Johansson will also be connected to many other people. One in particular, how about Adam Driver? Remember that guy? The guy from, you know, he was Kylo Ren. They were in that movie. I didn't see it about two people that yell at each other in an empty room. I saw it in the memes. Marriage, something like that. Anyway, Scarlett Johansson was in that movie with Adam Driver, along with many other people, of course. And Adam Driver has been in many movies, so he's got many other connections. But actually, I looked this up. Chris Evans and Adam Driver have not been in a movie together as of 2020, March 2020. And so there is no edge from Chris Evans to Adam Driver, right? No edge there. But there are many edges, many other vertices in this graph, okay? Can we talk specifically or just think about what does the degree represent in this graph? Remember, I said at the very beginning, the definition of degree is how many edges are hitting each vertex. So, what if I told you the degree of the Chris Evans vertex is 3? Or what if I said it was 300? Or what if I said it was 1,000? What do you think? Does any one of those sound reasonable? Is it possible that in the real graph, Chris Evans' degree is 3 or 300 or 1,000? What does the degree represent? What it represents would be how many edges, and we said there's an edge when this actor has been in a movie with some other actor. So what the degree represents is how many other actors they worked with. So what is Chris Evans's degree? I don't know what it is, but it's definitely not 3, right? That was one of the options I said before. If Chris Evans's degree was 3, that would mean that he was only in movies with 3 other people, which is not true. Even in one of those Marvel movies, he was with like 100 other stars, right? So Chris E's degree is, can I just say, it's pretty high, right? It's not 3. It's something more like maybe 1,000. I don't know. How you have to just think about how many other actors has Chris Evans ever been in the same movie with? It's a lot. Probably maybe not 1,000, but can I say several hundreds? Right? And same with Scarlett Johansson, and same with Adam Driver, right? Maybe Adam Driver's is lesser than these other two, although I don't know. The degrees would be several hundreds. All right, one more sort of imagine a graph and tell me about it. How about the vertices of this graph are all Fairfield University students, our dear university. All Fairfield University students. Remember that place? You used to go there every day? You used to like live there? The vertices are all Fairfield University students, and let's say an edge. Let's just imagine that all Fairfield University students are coming from the U.S. I know that's not true. Let's say an edge between any students from the same state. You know, before they came to Fairfield University, they lived somewhere. The same United State, the same U.S. state, all right? Some of y'all from Connecticut originally. Some are not, all right? So if you have, say, two people on the graph, right, there would be an edge if they're both from the same state. Can you think about what such a graph would look like? I will ask you. Is it connected? Here are some things to think about. What else can I ask? Think about yourself. What is your degree in such a graph? Do you think it's like, you know, I mean, you probably don't know the exact figure, but is it like 5 or is it like 100 or is it like, 1,000? These are the questions that I would like you to think about. I'll give you a moment. Think about it. Is it connected? What's your degree? Think about it. All right, I hope you thought about it, and I hope you decided. The answer to the first question is no, it is not connected. That's because in this graph, you have a whole bunch of students from a particular state, and there will be edges between all of them. So let's say we're going to have, let's imagine that there's like, say we have, how many students are there at Fairfield? Something like 4,000, at least undergrads. Let's just focus on undergrads. Is it four? Let's say there's 4,000. I don't know. I just work here. Let's say we have, out of those 4,000, let's say 800 of them from Massachusetts. All right? I don't know how accurate that is. It's approximately accurate. What that looks like in the graph is you're going to have all these 800 people, and every one of them will be connected to every one of them, the other ones, right? Every single person among this 800, they are all connected to all of the others, and they are not connected to any others. So these guys, everybody is connected to everybody else. This is like all the people from Massachusetts. They are in one piece of this graph, and none of those people have any connections to anybody in another state. So we also have all the people from Connecticut, which is probably even more than the ones in Massachusetts. So they also have a blob of students who come from Connecticut, and nobody in the Massachusetts is connected by an edge to anybody in the Connecticut group. All right, that means that this graph is disconnected. It has one chunk of all the people from Massachusetts, one other chunk of all the people from Connecticut, there's another chunk of people from New York, and every other state, right? Every state has its own little piece in this graph. So the answer, is it connected? No, it is not connected, because every whoever you're connected to is based entirely on what state you're from. And there is no way to get from one of these people to one of these people by following edges. All right, what is your degree in the graph? What you should be thinking about is how many edges are connecting to your dot, and your dot is somewhere in this graph, depending on what state you're from. I come from Massachusetts. I'm not a student, but let's imagine that I'm in this graph somewhere. I come from Massachusetts. My degree would be how many edges there are going into my dot. And if you assume what I said here, let's say we have 800 from Massachusetts, then my degree would be 800. There would be an edge from me to all 800 of these other people. And so my degree, if I'm from Massachusetts, would be 800. Really, this degree, whatever the degree is, it is equal to the number of other students from my state. So what is your degree? It is the number of other students. Studs. All right. Number of other studs from my state. All my students are studs, aren't they? Right? So it would be different for different ones of you. If you're from Massachusetts or Connecticut or New York, your degree is probably fairly high, in the hundreds, just because at Fairfield University there are so many people from those states. But if you're from Alabama, your degree is probably much smaller, maybe 10, maybe less than 10. I don't know how many students at Fairfield are from Alabama, right? Your degree is just the number of other students who come from your state and go to our beloved Fairfield University. All right, that's all the cute examples. I wanted to say one thing of technical content.